Welcome back to the Deep Dive. Today we are tackling a subject that is, well, without exaggeration, it's kind of the operating system of civilization.
That's a good way to put it.
I mean, it organizes your money, your medical records, your flights,
Yeah.
everything. We're looking at the relational database model.
It really is the mathematical backbone of the information age. And I know when people hear database, they immediately think boring digital filing cabinet.
Right.
But looking at the research for today, from Codd's original papers to modern theory, this isn't really about storage, it's about truth.
That's the angle. That's what I want to get into. Because
Yeah.
if you look at the history, especially in some of these sources like Database Design for Mere Mortals, you realize that before this model, the digital world was basically built on sand.
Oh, it was the wild west of data. They called it the before times.
Yeah.
Before the relational model, you had these flat file designs.
So just a huge text file or a
Yeah.
spreadsheet.
Exactly. Imagine a massive spreadsheet where every single rule is manual. The biggest problem was redundancy. Just the same information typed out over and over and over again.
Like a customer's address. If I order 5 things, my address is in there 5 times.
And that's where the chaos starts. Because, okay, what happens when you move?
You have to find all 5 of those entries.
And update every single one. If you miss one, just one, you now have what's called an update anomaly.
And the computer has no idea where I live.
None. Is it the old one? The new one? The system loses its grip on reality because the data contradicts itself.
It wasn't just flat files, though. The notes mention hierarchical and network models. They sound a bit more advanced.
There were attempts at structure, yeah. Hierarchical was like a strict parent-child org chart. Network models allowed a few more connections.
But they were still really...
You practically had to rewrite the software just to find the answer.
So into this messy, rigid world steps our protagonist, Dr. E.F. Codd.
Codd is the hero of this story. IBM, 1969. He wasn't just a programmer, he was a mathematician.
That's the key, isn't it?
It is. He looked at this mess of pointers and hard-coded links and just said, we can do better. He applied first-order predicate logic and set theory to data.
He built a system of logic, not just a better cabinet. And that's our mission for this deep dive. We're going to unpack that logic.
From the theory all the way to how we keep data safe when 1 million people are using it at once.
Okay, so let's start with the basics, the vocabulary.
Yeah.
Because we all say tables, rows, and columns.
We do. But if you read the purest sources, like the Introduction to Relational Database Theory, they'll stop you right there.
It's relations, tuples, and attributes.
Right.
Is that just academic gatekeeping, or is there a real difference?
It's a crucial distinction. A table, the way we picture it in a spreadsheet, implies order. Row 1 is above row 2. Column A is to the left of column B. But a relation is based on set theory. And in a mathematical set, order doesn't exist.
Like a bag of marbles. It doesn't matter which one you pull out first, the collection is the same.
Precisely. A relation is a set of tuples. And because it's a set, duplicates are, well, they're mathematically impossible.
You can't have 2 identical things in a set.
The math just forbids it. It forces a discipline that flat files never had. This ties right into Codd's information principle, his rule 1.
Which says, what? Everything has to be visible.
Exactly. All information in the database is represented in exactly one way, as values in a table.
So no hidden tricks.
No invisible pointers, no go-to memory address X. If the data exists, it is a value in a table, period. That decouples the data from the hardware.
Speaking of his rules, there are actually 13 of them, right? Numbered 0 to 12.
Yes, and he basically wrote them as a defense mechanism. It was a marketing war.
How so?
Vendors saw relational was the hot new buzzword, so they started slapping stickers on our old clunky non-relational products. Codd had to lay down the law.
I want to highlight Rule 12, the non-subversion rule. It sounds like something from a spy movie.
It's the security guard of the model. It says you can't use a low-level tool, like something that touches data row by row, to bypass the integrity rules.
So you can't use a backdoor to cheat the system.
Exactly. The integrity has to be absolute no matter how you access the data.
Then there's Rule 3, about nulls. I feel like this is the most misunderstood part of databases. I always just thought null was a 0 or an empty space.
That's the common mistake. But in the relational model, null is a marker. It means missing or inapplicable information.
So it's not a value, it's a lack of a value.
Precisely. If I have an employee and their date of birth is null, it doesn't mean they were born in the year 0. It means we don't know.
Right.
And the math has to account for that unknown. If you add 10 to a null, The answer isn't 10. The answer is null. Because 10 plus I don't know is still I don't know.
That actually makes perfect sense. Okay, so we've got the theory. Now, how do we design these things? The blueprint. This brings us to keys and normalization.
This is the heart of it. The core of any relation is the key.
The primary key.
The anchor. It's the unique identifier for a tuple. Student ID, social security number, whatever. It has to be unique, and it cannot be null.
And the foreign key is the bridge.
That's the glue. A foreign key in one table points strictly to the primary key of another table. Let's use that agents and clients example.
Okay.
You have an agents table. Each agent has a unique agent ID. That's the primary key. Then you have a clients table.
And you need to know who represents whom.
Right. So instead of typing the agent's name into the client record, which is redundant, you just put the agent ID in the client's row. That agent ID becomes the foreign key.
And that link lets you normalize the data.
Exactly. Normalization is about isolating themes. You want what's called the ideal table.
Which represents just one single subject.
One subject, an object or an event. And this is crucial. No multi-valued fields.
Explain that one. That sounds like a mistake I see in spreadsheets all the time.
Oh, it's the classic blender. Imagine a student's table. You want to list the classes they're taking. The bad way is to have one column called classes and just type math, science, history into one cell.
It looks fine to a person reading it.
But to a machine, it's garbage. You can't sort it. You can't count students in science. It violates the atomic nature of data. One cell, one thing.
That's the many-to-many problem, right? Students have many classes, classes have many students. So how do you fix it?
With a linking table, you create a new table, maybe call it enrollments. It only has two important columns, student ID and class ID.
So each row in that new table is one student enrolled in one class.
That's it. If a student takes 3 classes, they have 3 rows in the enrollments table. It's clean, efficient, and lets you query from either direction.
That's the beauty of it. By breaking things down, they get more flexible. But then you have to make sure those links don't break.
Yeah.
This is referential integrity.
This is about keeping promises. If that enrollments table says student 101 is in class A, then student 101 must exist.
And class A must exist.
Right. So if you try to delete student 101 from the system,
But they're still enrolled in classes.
the database steps in. It acts like a bouncer. It throws an error. Cannot delete this record. Other records depend on it. It stops you from creating a contradiction. That's the restrict rule.
But we can tell it to do something else. We can tell it to use cascade.
On delete cascade, it is powerful and dangerous.
Mm.
If you set that rule, deleting the student record will automatically trigger the database to hunt down and wipe out every enrollment, every grade, every record tied to that ID.
Sure.
It keeps the data clean, no orphans, but you have to be very sure. Accidentally cascading a delete on a customer could wipe out years of financial history.
That's a resume-generating event.
It is. So we've structured the data, locked
Yeah.
it down. Now we need to get it out. We need to talk about the join.
The art of the join.
This is where set theory pays off. We're taking separate relations and computing a new set based on how they connect.
The notes start with the Cartesian product.
The cross join, it's the theoretical starting point. If you join table A and table B with no criteria, the math says, combine every single row of A with every single row of B.
So 100 customers times 100 products is 10,000 rows.
Most of which are total nonsense. But that's the canvas. Then we apply a filter, and that filter gives us the inner join.
The inner join is just the overlap, the middle of the Venn diagram.
Exactly.
Yeah.
It only returns rows where the keys actually match. So if you have an employee, John, who hasn't been assigned a department yet, and you do an inner join,
John disappears from the report.
he's gone
Yeah.
because he doesn't match,
Yeah.
which can be a problem if you're trying to see all employees.
So that's when you use an outer join.
Specifically, a left outer join. You tell the database, prioritize left table employees. Show me everyone. If they have a department, show it. If they don't, just put it on there.
And a right outer join is just the reverse. Prioritize the other table.
Correct. It would show us the marketing department even if no one works there yet.
There was one other case, the self-join. That sounds a little introspective.
It's for hierarchies. Imagine an employees table. You have a column for manager ID. Well, the manager is also an employee. They're in the same table.
So to get the manager's name.
You join the table to itself. Pretend it's 2 separate copies. You link the employee ID on one side to the manager ID on the other. It's a bit mind-bending, but it's how you walk up a chain of command.
Okay, so we've covered structure, integrity, retrieval. But the outline calls this next part the deepest dive. Concurrency.
This is where the rubber meets the road. The problem is simple. What happens when two people try to change the same data at the exact same millisecond?
The classic last concert ticket problem. I click buy, you click buy. Who gets it?
If the database is careless, it might sell it to both of you, or take my money and give you the ticket. We need serializability.
The gold standard.
Yes. Serializability is the guarantee that the final result is the same as if the transactions had happened one after another in some strict order. If a system is serializable, it's perfectly safe.
But perfection is expensive.
Incredibly expensive. It requires strict locking, making everyone wait in line, so databases offer isolation levels. We trade a little bit of safety for a whole lot of speed.
Let's walk through them. Read committed.
That's the default in many systems. It just says you will only see data that has been officially saved. You won't see someone's half-finished work. But if you read a row, then I change it, then you read it again. You'll see two different things. It's not stable.
Okay, then there's snapshot isolation. This one feels more intuitive to me.
Think of it like a photograph. When your transaction starts, the database freezes time just for you. You're working on a snapshot of the world as it was at noon. Even if I'm changing things at 1 second past noon, you don't see it.
That sounds safe. You're in your own private bubble.
It's mostly safe, but it introduces this very weird anomaly called right skew.
Give me an example of that.
Okay, let's say we have a joint bank account with $100 in it. The rule is the balance can never drop below zero.
Simple enough.
We both check the balance at the same time. In my snapshot, I see $100. In your snapshot, you see $100.
So we both think we can withdraw $100.
Right. And the database lets both transactions go through because in each individual snapshot, the rule wasn't broken. The result, the account is now at minus $100. We broke the system.
Wow. Because individually, we were both right, but together, we were completely wrong. So how do you fix that without slowing everything down? This is where robustness comes in.
Robustness theory is about proving that a specific workload can run safely on these weaker levels. Researchers can look at a process like order entry and prove mathematically, for this specific set of actions, snapshot isolation is safe. You won't trigger a right skew.
So it's a calculated risk. You take the shortcut because you've proven you won't crash the car.
Exactly. It lets systems run thousands of times faster while maintaining integrity for that specific use case.
We have gone from flat files to robustness theory. That was a journey. But I want to land on this final provocative thought from the research about the relational model itself.
The reality check.
It says that SQL, the language that runs the world, is an engineering approximation of the model.
That's a polite way of saying it's a compromise. Cod was a theorist. He wanted mathematical purity. SQL is a tool for the real world.
What did he not like about it?
Well, he hated that SQL allowed duplicate. Remember, sets can't have duplicates. He hated that it cared about column order. And his ideas about nulls were way more complex than how SQL handles them.
So the tool we use isn't the pure math. It's a practical adaptation.
It deviates, but it works. It strikes a balance between the rigid logic of set theory and the practical needs of building software. It might not be pure, but it's powerful.
And that's really the takeaway, isn't it? The relational model is a triumph of logic. By organizing data into these sets, by enforcing strict rules, we created a system reliable enough to run the global economy.
It's invisible to most of us, but every time you swipe a card or book a flight, you're relying on Cod's logic to make sure the world stays consistent.
So here's a final thought for you listening. We talked about normalization breaking things down to their purest form. Look at your own data. A spreadsheet for work? How you organize contacts? Is it normalized? Or are you living in the before times, risking anomalies every time you update a phone number?
And remember, next time a database gives you an error saying you can't delete something, don't get mad. That's just referential integrity saving you from yourself.
Thanks for listening to The Deep Dive. We'll see you next time.